Imagine, just for tonight, a single soft voice guiding you. A journey through the cosmos. A story woven from starlight and, well, silence.
We're drawing tonight from the quiet knowledge held in the basics of spaceflight.
But this isn't a lecture. Think of it more like a dream we're sharing.
Mm-hmm. A kind of poetic drift through the universe, letting the mind wander.
Let's begin with something familiar yet vast.
Our sun.
Our sun.
Yeah.
But maybe picture it differently tonight, not as this, blazing giant right above us,
That's it.
as just one tiny spark, one among, well, countless stars scattered across the immense dark of our Milky Way galaxy.
Just one, and the nearest one, Proxima Centauri.
Right, our closest stellar neighbor, a little red dwarf star, and it's 4.2 light years away.
4.2 light years. That distance. It's hard to grasp, really.
It means the light from it, the light you might see if you look tonight, actually started its journey over 4 years ago.
Wow. And it's not just Proxima, is it? We know there are other suns out there. Oh, absolutely. Astronomers have found hundreds, thousands now of other stars with their own planets, exoplanets.
Many of them quite different from ours, right? Like huge gas giants.
Yes, lots of gas giants. Sort of like bigger versions of our own Jupiter. Makes you wonder how common our little solar system setup really is.
And our sun, our whole system, it's not just sitting still in space, is it?
Not at all. It's actually moving. We're all on this incredible journey
Journeying where?
through our local stellar neighborhood, drifting at about 100,000 kilometers per hour.
That's incredibly fast. Through what exactly?
Through these very thin clouds of interstellar gas, mostly hydrogen and helium.
So we're sort of nestled inside one of these clouds right now.
We are. It's called the local interstellar cloud. It's relatively warm, partly ionized. Our little home is wandering through it.
Let's travel outwards then, in our minds, far beyond the planets we know.
Okay, way, way out. Maybe 50,000 astronomical units away. That's, well, nearly a light year from the sun.
What's out there?
We think there's a huge sphere of icy bodies, comet nuclei. It's called the Oort cloud.
We haven't actually seen it though, right? It's hypothesized.
Exactly. We infer it exists because it seems to be the birthplace of those long-period comets.
The ones that take thousands of years to orbit the sun.
Those are the ones. Their orbits sometimes get nudged, maybe by a passing star's gravity.
And that sends them falling inwards towards us.
That's the idea. Sent on these incredibly long journeys towards our sun. A vast frozen reservoir at the edge of everything.
Like a cosmic attic full of ancient ice.
Yeah.
And there's something closer in too, isn't there? Another source of comets.
Yes, closer in, beyond Neptune, we have the Kuiper Belt.
That one's more like a disk, right? Not a sphere.
That's right. A flatter, disc-shaped region, stretching from about 30 AU out to maybe 100 AU.
And it also holds icy bodies.
Yep. Another reservoir of comets. This is where many of the shorter period comets come from, the ones that visit more often.
So we have these reservoirs of ice far out, but the sun itself, it's not passive. It's sending stuff out constantly.
It is. It's always exhaling, you could say, a stream of charged particles.
The solar winds.
The solar wind, mostly protons and electrons flowing outwards. Near Earth, it's moving at about 400 kilometers per second. Pretty fast.
And this wind, it does something significant, doesn't it? It creates a sort of bubble.
It does. A vast bubble around our entire solar system. We call it the heliosphere.
So the sun's breath creates our local space environment.
In a way, yes. It pushes back against the interstellar medium.
You choose.
Basically the gas, dust, and cosmic rays. The general stuff that exists between the stars. The collective winds from other stars, too.
So our heliosphere is like our solar system's protective shield as we move through the galaxy.
Kind of, yeah. It marks the boundary of the sun's dominant influence.
And the edge of this bubble where our solar wind meets that interstellar stuff, That's the heliopause.
That's the heliopause, the boundary zone.
What shape do we think it has?
Well, because the sun is moving through the interstellar medium, it's thought the heliopause is probably shaped like a teardrop, stretched out behind us.
Like the wake behind a boat moving through water.
Something like that, yeah. There might even be a bow shock out front, though scientists are still debating the details. It's amazing to think about.
It really is. Our whole system carving its path. Now, shifting scales. Way bigger. There's something that fills all of space, isn't there? A kind of echo.
Ah, yes. The cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang.
That's often how it's described. A faint whisper from the universe's birth. It permeates everything. Everywhere.
Left over from a time before stars or galaxies even existed?
Exactly. From when the universe was incredibly hot and dense, now it's cooled down.
How cold is it?
Incredibly cold. Just 2.7 Kelvin. That's barely above absolute zero. A universal chill carrying echoes of creation.
Wow. Okay, let's come back into our solar system for a moment. Gravity. The sun dominates, right? Mass-wise.
Oh, absolutely. The sun holds more than 99.8% of all the mass in the entire solar system. It's the gravitational anchor.
Everything orbits it because of that massive pull.
Everything. Planets, moons, asteroids, comets, they're all held in its sway.
But the planets, even though they're tiny in comparison mass-wise, they hold most of something else, don't they? Momentum.
Us. That's a fascinating point. The planets, especially the giant ones, hold the vast majority of the solar system's angular momentum.
Angular momentum. That's like the momentum of spin or orbit.
Kind of, yeah. It's the measure of an object's tendency to keep orbiting or spinning. This distribution is key to the stability of the whole system.
We can actually use that with spacecraft.
We can, and we do. It's called a gravity assist. We can use a planet's gravity and its orbital momentum to slingshot a spacecraft, give it a speed boost.
Like catching the current of a great river.
Exactly. A tiny ship borrowing momentum from a giant planet. It saves enormous amounts of fuel for exploring the outer solar system.
Clever. No temperature. It obviously gets colder as you go out from the sun.
Generally, yes. Big contrasts. Mercury, close in, can have surfaces hot enough to melt lead.
While out at Neptune, its moon Triton
is incredibly frigid, hundreds of degrees below 0 Celsius.
But there are extremes even within planets or the sun, right?
Oh, absolutely. The core of Saturn, for example, is estimated to be around 15,000 Kelvin, hotter than the sun's surface.
And the sun's core.
That's off the charts, about 15 million Kelvin.
15 million. And yet, even in supposedly empty space, within that heliosphere.
Right. The plasma, the charged particles of the solar wind, it's extremely low density, hardly any particles per cubic centimeter. But those few particles can be incredibly energetic, technically very high temperature.
But it wouldn't feel high because there's so little of it.
Exactly. Not enough particles to transfer significant heat to, say, a spacecraft. It's a different kind of hot.
Fascinating. And all these orbits, this movement, it follows rules, doesn't it? It's not random.
Not at all. It's a beautiful choreography. Planets move in predictable paths called ellipses.
With the sun not quite at the center, but at one focus point of the ellipse?
Precisely. And there's that elegant rule Kepler discovered.
About equal areas and equal times.
Yes. A line connecting a planet to the sun sweeps out the same amount of area in the same amount of time, no matter where the planet is in its orbit.
Which means it moves faster when it's closer to the sun.
And slower when it's farther away. A cosmic ballet governed by gravity's laws.
And despite these immense distances, these light years we talked about, we can still communicate, send messages.
We can. Using electromagnetic radiation radio waves mostly, which travel at the speed of light.
The ultimate speed limit.
The ultimate speed limit. It still takes time, of course, minutes or hours for signals to reach even the planets in our own solar system.
And we have ways to listen for signals coming back from spacecraft.
We do. Networks of huge radio antennas around the world, like the Deep Space Network.
listening for those faint whispers from our robotic explorers far, far away.
And sending commands back across the void. It's our link, our conversation across the light years.
So, dear listener, as the stars wheel silently overhead tonight, hold on to this story.
This grand, unfolding tale of wandering stars, whispering clouds of gas, and the delicate, intricate dance of gravity.
May your dreams be touched by the soft glow of distant galaxies, the gentle rhythm of cosmic time.
And perhaps wonder, what other secrets does this vast, quiet universe hold?
Perhaps that is a story for another night.